Hey everybody, welcome. My name is Scott, and today we're going to be solving the house robber problem on Leetcode. We're going to be solving this problem using dynamic programming. So let's set up the problem definition. In this problem, we are a house robber, and we are starting at the beginning of a street of houses. And we are looking to maximize the amount of money that we rob from the houses on this street. So, how are we going to do that? Well, we have a couple rules. Really, one rule. These houses have an alarm system set up, a rather interesting alarm system, where if we rob houses that are adjacent to each other, the police are warned, and we're caught and we go to jail for house robbing. And that is the constraint that we have to work under. Step one in establishing a solution for this problem is figuring out a recurrence, where we write a mathematical equation which writes the solution of the large problem in terms of solutions to the smaller problem. So what is the applicable recurrence for this problem? Well, when we're standing at the beginning of this street, we have two options. We're standing at the beginning of the street. We can rob the first house, which means we cannot rob the second house. Or we can skip the first house and go rob the second house. So we can start to see what the recurrence will look like from that definition right there. If we want to maximize the amount of money we're going to rob from the houses on this street, then what we're going to want to do is take the maximum of robbing the first house plus robbing all the houses starting with the third house, because we can't rob the second house if we rob the first house, and the maximum of robbing all the houses on the street starting from the second house. In that case, we don't rob the first house and we go straight to the second house and start there. And that's the recurrence. The recurrence is just the maximum profit we can gain from robbing all the houses on the street starting from the first house is equal to the maximum of the amount we gain from robbing the first house plus the recursive call, the maximum amount of money we can gain from robbing all the houses starting with the third house on, and the maximum amount we can gain from robbing all the houses on the street starting from the second house. Now that we've got our recurrence, we can go into the code here and implement our recurrence. Now we're going to set up a helper function. It's kind of becoming a recurring theme here. Our helper function is going to take in the nums, which is an integer array holding the amount we gain from robbing each house, and an integer, which we'll set at 0 at first. So let's set up the helper. As a parameter of the nums, and then an integer which we'll call house. What the house parameter represents in this problem is the house that we're starting from. When we pass in 0 right here, we're saying we're starting at the first house. That's where we start the problem out. As with any recursive algorithm we write, we need some way to bottom out our recursion. We need a base case. In this case, the base case is if the house is greater or equal to nums.length. All that means is in this case, we're out of houses to rob. No more houses can be robbed. In that case, we'll return 0. So you can think about that base case really quick. If we send in 0, saying we're starting at the beginning of the street, however that street's empty, there have been no houses built on that street, we just return 0. And then we will just set up our recurrence. I'm going to go ahead and store the recurrence in a variable this time. It's going to be the max of nums of house, so the amount we get for robbing the first house, plus our recursive call, pass in nums, and then we pass in house plus 2. What house plus 2 signifies is that we've skipped the next house because we robbed the previous house. We can't rob the next one or else the alarm will go off. And the other argument to the max is just a recursive call for house plus 1. So we don't rob the house we're currently at, we just go to the next one because we can rob that one. Since we haven't robbed the previous one, the alarm won't go off. And we're going to return that answer. So let's run our code, see if we have any syntax errors floating around or anything. We do. No, we need to return this answer. Alright, so we've got this rather interesting case right here, where these are the numbers representing the amount we can earn from robbing each house, and the expected answer was 38. We got 38 as well. So we maximized our profit from robbing this street of houses right here. Alright, however, let's go ahead and try to submit this solution. Uh-oh. Time limit exceeded. Really long house, a lot of houses. We ran out of time. We started robbing at night because that's what robbers do. And we ran out of time. Daylight came around, everybody woke up. We couldn't rob any more houses. Okay. So what's the problem? Well, this is an exponential runtime solution in this recursive algorithm, which is computing the same information over and over and over again. We can see that pretty easily. If we ask it to compute the maximum we can get starting from 1 and the maximum we can get starting from the second house, each of those will try to figure out what the answer is for starting from the third house. And then that will make calls to figure out what the maximum is starting from the 4th, 5th house, so on and so forth. And all those calls will be duplicated. We're doing a whole lot of extra work in here. So this is where dynamic programming jumps in to save the day. And how are we going to do that? Well, first thing we're going to do, set up a data structure which will remember answers we've already seen. Okay? So we have a hash map, integer to integer, called memo, and that is the data structure that's going to remember things that we've seen. Now when we're implementing the dynamic programming part of the algorithm, the first step is always, have we seen this answer before? So, does memo contain key of house? House is just an instance of the problem. It represents starting from that house and robbing the remaining houses on the street. If it does, return memo get house. Okay. And I conveniently left this one line open right here because all we have to do at this point, now we've gotten down here, which means we have not seen this answer yet, we've not yet computed it. We compute it as we did before right here, and then all we have to do is store that answer. And voila, that is all the dynamic programming that goes into this problem. We set up a data structure that remembers answers we've already computed. When we come into our recursive function, the first thing we do is check that data structure and say, have we seen this answer before? Have we seen this problem before? If so, we know the answer already, we return the answer. If we have not seen it already, we compute it as before, and then we just remember what the answer was. Let's run the code, make sure everything syncs up, 38 and 38. Now remember, we timed out when we submitted earlier without our dynamic programming solution, right? So let's submit this one. And there we have it, accepted solution just like that. And that's all there is to dynamic programming in problems like these. So let's run through what we did really quick. Analyze the problem. We set up a recurrence, which is a mathematical equation which describes the solution of the larger problem in terms of solutions of the smaller problem. We then took that recurrence, turned it into a recursive function in code. Once we had written that recursive function, which is algorithmically correct, we tried to run the code. However, that is an exponential runtime solution, and if you don't know a whole lot about asymptotic analysis, exponential runtime solutions are doomsday type stuff. That you could give the computer a big enough problem that literally the universe has not existed long enough for the computer to come back with an answer. It'll never work. So we can give it a small number of houses, but it'll work for those. But any problem of real size, it'll never figure it out. So while it's algorithmically correct, the time complexity makes it such that it's useless. And then all we have to do to make our algorithm useful is just use dynamic programming. Sounds like something crazy, but all we did was set up this data structure which remembers answers we've already computed. Inside our recursive function, we first check to see if we've answered this problem already. If we've answered the problem already, we just return the answer. If we haven't, we compute the answer as we have before, and then we just store it. That's really all there is to it. Hopefully you're starting to see the pattern that we've been following along here. And we'll be following up with this later. There's a House Robber 2 problem on here which adds a couple of wrinkles into the problem, but nothing too crazy. So hopefully you learned something. We'll catch you next time.